Yes. So last class we were discussing about ripple counter. Mm, yes. Wait. Okay. Yes. This is what it is. So in this case, we understood that the binary ripple counter is converted into what is known as a BCD ripple counter. So the point here is that um, the clock pulse is applied only to the first flip flop. Clock pulse will be applied only to one of the four flip flops. It need not be like a first something like that. See, ultimately anyway they are going to work in series. So the clock pulse will be applied to one of the flip flop, and the output of that particular flip flop will be there is output means normal output will be applied as a clock input to the next flip flop. Okay, this is the normal structure. But to generate BCD ripple counter, so we have to stop the counter. Otherwise, it will start from 0000. It will go up to 4 bit counter. The initial count, if it is 0000, it will go up to 1111. Okay, whereas we have to stop at 1001, so that it is a BCD counter. Total number of states is 10, including the first state of 0000. Okay, so for that, the design is like this. If you see this, this timing diagram. This timing diagram explains everything. So here it is, yes, something like this. So as the first flip flop toggles, to which the clock pulse is applied. This is the first flip flop. This is the second, third, and fourth. Okay. So when the flip flop, as we can see, and also we can observe in the diagram, because last class we discussed this, it is a negatively triggered flip flop. Negatively triggered flip flop. That means it will change the state when it will go from 1 to 0. So this transition will trigger the flip flop. Okay. So thereby, so we have four flip flops. The first flip flop gets the clock pulse. So when it goes from 1 to 0, 1 to 0 transition will trigger the second flip flop to go from 0 to 1. Okay. Similarly, the second flip flop, when it goes from 1 to 0, the third flip flop will go from 0 to 1 transition. Okay. So we call this as a transition. Okay. So yeah, here it is. Okay. So these transitions are important. Okay. Now, when the third flip flop output, Q output, normal output, goes from 1 to 0, there is a negative transition, falling edge. The fourth flip flop will go from 0 to 1. Fourth flip flop will go from 0 to 1. Okay. So thereby, if you observe this region, there is starting from the Q8. Q8 means the MSB. Q8, Q4 is a weightage, binary weight. I think we all know binary weight. There is 2 power 3. Okay, 2 power 3 gives 8. 8 binary weight 8. 2 power 2, 2 power 1, 2 power 0. So the weightage is 8, 4, 2, 1. So based on this, the output of the flip flops are named as Q8, Q4, Q2, Q1. This we saw in the last class. Okay. Now what will happen is, okay, if observe this part of the output. Okay, here the output is the 1001. Okay, so it has started from the first state of 0000. If I can change the color so that okay, so the first state is 0000. So as the clock transitions from high to low, the first flip flop will go from 0 to high. Okay, there is a rising edge. So this continues. Okay, when it reaches the count of 9, there is 1001. The next state should not be 1010. I'll erase all this. I think this we by now we have understood. What is the weightage of the each bit. So the next state for a binary ripple counter is 1010, but we don't want this state to happen because it will not be a BCD counter. Okay, the next state should be 0000. Okay, So now 0 0. Okay. In this case, observe this point base. There is in the next instance the when the clock pulse count pulse when it goes from high to low, the Q1 will transition from 1 to 0, not a problem. This is fine. Okay, this should be 0 anyway because we are expecting that to be 0. That is LSB. We are expecting the LSB to be 0. That's fine. That's okay. But when it comes to okay, now when it comes to the next bit, okay, there is the no the uh, when Q1 goes from high to low, okay, the Q2 will go from low to high. We need to stop this. Okay. So initially, what is the condition of Q2? 0. So initial condition is 0. Let us note this. Okay. And okay. So what we want at Q2, what we want at Q2 input is Q2 flip flop input is that it should remain 0. It should remain 0 so that if it go if the previous output goes from 1 to 0, the output will go from 0 to 1. The output of the third flip flop will go from 0 to 1. We need to stop this. Okay. So for that, what we need to do is the input should be kept at 0. It should never allowed to go to 1. It should never allowed to go to. It should not be allowed to go to 1. Okay, that's one thing. Okay, and the next thing is what is the other transition is which is happening at this point. Okay, and when it goes from, there is Q1 goes from high to low, there is a possibility that Q2 will go from low to high. Okay, so this we need to stop because this should be 0. That's one thing. Okay, now this when this Q2 goes high and at after some time when it goes low, Q4 will go high. Q4 will go high. Okay, Q8 is not an issue. Q8, the point with the Q8 is it continues to for a few more cycles. How many cycles? How many more cycles? For few more cycles, Q8 will continue to be at logic 1. Why? Because if you see this the truth table, somebody is on the line. Just a second. Okay. Okay. Now, so when we see this truth table, it is something I need to take the. Okay, I'll take the pic. I'll forget. Anyway, no problem. Okay. So when we see the binary ripple counter, it starts from 0000. It goes up to 1111. Okay. If you see the nature, this is Q8, Q4, Q2, Q1. Okay. For a binary 4-bit binary ripple counter, the Q8 will change the state only once. Okay. For half of the transitions, it will remain 0. For another half, it will remain 1. That means almost for 8 states transitions, it will remain 1. Not an issue. Okay. So thereby, uh, we don't have any issue with the Q8. Q8 is not an issue because it will continue to remain 1. Not an issue because it will never transitions. Not a problem. Okay. So what is expected is Q2 output should not be allowed to go to 1, and Q3 should not be allowed to go to 1. Okay. So for that, what we have to input should be 0. Basic ideas input is 0. So initially these two are 0 0. If you see this state, this point of the output, it is a binary simple binary ripple counter. So what we see here is 1001. That is the final state of a BCD ripple counter. For the next state to be 0000, the input for the second and the third flip flop, that is Q2 and Q4, should be 0 so that it does not transitions to 1. So for that, what we can do is let us jump back to the circuit diagram. Yeah, here it is. Okay. So what is done is I need to fit this. Okay, somebody is on the line. Okay, yeah, here we go. Just hold on a second. I need to take this, the attendance. So I need to go to the paint. Each class will we need to submit this attendance. Here it is. I'll save it later. No problem. Maybe without this is better. Huh? I need to change the layout so that it's already tiled. So more number of is possible. No, it's not possible. Okay. Issues. Here we go. Okay. So okay. So what we observe here is the output of the first flip-flop, I need to fit it to 85. Okay, output of the first flip-flop, that is Q1, is fed as a clock input to the next stage. This is okay. Now for Q2 and Q4, the condition is it should never go to 1. After the final state of 1001, these two should never go to 1. So for that, what is required is Q2 is ANDed. Okay, Q2, if you can observe, it is applied as a clock pulse to the next stage. Of course, why? Because you should transition. Whenever the Q2 changes the state, Q4 should also change the state. Not a problem. Okay, but for Q4, there is Q2 and Q4, which is equal to 00. Okay, is applied as a input AND gate using AND gate. It is applied as an input to the last flip flop, so that it is forced to remain 0. It is forced to remain because it is 1. See, it is 1. So for this, just now we understood in this truth table, there is for another 8 cycles, Q4 will be, Q8 will be 1. We need to force this to 0. We need to force this to 0. Okay. How to force that to 0? Very simple. Use an AND gate. The input for this AND gate should be 0, 0. We could have taken from Q1, not an issue. But Q1, what happens with the Q1 is the problem is, it will alternatively change the state. So the best is the Q2 and Q4. So the Q2 and Q4 is applied as a input to the AND gate. The output of the AND gate is applied as a which input? That is very important. J input to the JK flip flop. So the fourth flip flop. So when it is 0, okay, the output Q8 is forced to go to 0. Initially it is 1, it is forced to go to 0. Okay, and then after reaching the count of 1001, that is the final count of a BCD counter 1001. Q1 anyway changes to 0, not an issue. Okay, Q2 will remain 0. Okay, because see Q2, what happens is that uh, okay, okay, one more observation for Q2. This I missed it. The complement output of the fourth flip flop, that is Q8, is applied as a J input to the second flip flop. Why it is so? Because let's observe this. Yes, here it is. Initially, at this point of time, that is in this the timing diagram is very important. Timing diagram speaks a lot of things. We should carefully analyze. When Q8 is 1, normal output is 1. What should be Q8 dash? Q8 dash should be 0. Q8 dash should be equal to 0. Okay. So thereby, when this Q1 goes from 1 to 0, Q2 otherwise normally it will go from 0 to 1. Whereas if this Q8 dash of the last flip flop, if it is applied as an input to the Q2 that is 0 input, it will force the Q2 to go to 0, remain 0, not go to 0, sorry, it will remain 0. It is forced to remain 0, very simple. Okay, so that's how we have made sure that Q2 remains 0. Q1 will anyway not naturally Q1 will become 0. So the problem is solved. Okay, if Q1 is 0, Q2 is forced to remain 0. If Q2 does not change the state, Q4 will not have a problem. When the Q4 will change the state only when the Q2 goes from 0 to 1. I'm sorry. When it goes from 1 to 0, there is no chance of going from 1 to 0. So Q4 is not an issue. But the problem is with Q8, because for Q8 it is already 1. It will remain normally in the normal 4-bit binary ripple counter. It will remain 1 for 8 more cycles. It will remain 1 for 8 more cycles. So we need to force it to 0. Okay, so thereby what is done is the output of the Q2, that is 0, which is forced to remain 0 because of Q8 dash, and Q4, normal output of Q4. These two are ANDed, and the output is applied as a the output is applied as a the J input for the Q8. Okay, when it is applied as a J input for the Q8, the Q8 is forced to go to 0. From 1 it will go to 0. Very simple. Okay. So based on this analysis, the obvious question is how do we know whether it goes from 1 to 0 or AND gate or OR gate, which gate to be used? Okay, So that comes from the basic design. So for that, we need to have the understanding of the the flip flops. So and hence we get this structure. Okay. So the complement of the Q8 dash, the complement output of the fourth flip flop is given as a J input for the Q2 to force it to go to 0. The first flip flop is anyway 0, and the Q2 is 0, which is applied as a clock input to the next state, which will continue to force which will retain Q4 at 0, not a problem. So when Q2 and Q4 are ANDed and given to J input, both are 0, 0, output is 0, J is forced to go from 1 to 0. Okay, so the initial state now will be the next state. After 1001 will be 0000. Okay, so that's how we'll convert a 4-bit binary ripple counter which has 16 states into, that is 4-bit binary ripple counter with a 16 states into 4-bit BCD counter 4-bit BCD counter with 10 states That's how it is. That's okay. So that's about BCD counter. So this the same thing is explained here, and the slight modification of this BCD, ripple counter. We can see that in this diagram. Let us look into this diagram. Block diagram of a 3-decade decimal BCD counter. Okay, fine. What is 3-decade decimal down? Decimal counter. Okay. So for a 3-decade decimal down counter, so what is required is, so there are three. Okay, let us say if only one counter is used. Okay, let us say only one counter is used. What we get is 0000 up to 1001. Okay, that is 9 state. That is from 0 to down to 9. Okay, let us say we want a multi-digit counter. So that is we want to go from 00 to 99. Okay, so for that what we have to do, we can use one more counter, one more BCD counter, BCD binary ripple, sorry, BCD, I wrote wrong. Okay, BCD ripple counter, which will again go from 0000 up to 1001. Okay, 1001. For 3-bit binary count BCD counter, BCD ripple counter, one more BCD 3-bit 4-bit BCD counter, which will go again from 0000 up to 1001, which gives 9. Okay, but when we interface like this, observe this. How does the count should start? Okay, so the count first, the LSB least position counter will start the count 0 to 9. When it reaches 9, the next counter should start. When the second counter will starts from 0, it will go up to 9. Once the second counter reaches 9, the third counter should start the count, which again goes from 0 to 9. Okay, meantime, when the first counter started from 0, it went up to 9, the second counter will start. When the second counter starts, that is when it is 0. Okay, when it becomes 1, the lower counter should continue the count. It should again start from 0. Again, it should go to 9. Okay. Likewise, when the second counter becomes 9, it will start the third counter should start. When the third counter starts, the second counter should continue to count the clock pulse. Okay. So thereby, what is required here is, okay. So the first BCD counter, BCD ripple counter, 10 power 0 digit. Why 10 power 0 is because it will count from 0 to 9, lower digit. Basically it is lower digit. Okay, so when Q8, okay, reaches 0, basically if you observe this timing diagram, this is very important. Why Q8? Why not? Maybe you could have connected Q4 itself. Why Q8? That let us understand. If you observe, let's observe this. The Q8 is applied as a clock pulse to the next flip flop, until and unless Q8 changes the state. What is the initial count? Initial count, by the way, initial count is 0000. Okay, and the final count is 1001. Okay, if you observe this Q8, this is Q8. Q8 will change the state only once. Okay, it will go from 0 0 up to 1000. Next it will go from go to 1001. Next state of q8 is 0. Okay, when the q8 goes from 1 to 0, that falling edge will trigger the second stage of the counter. That means it acts as a clock pulse to the second stage of the counter, and the second stage of the counter starts the first. It will treat it as a first clock, and it will start the counter. Please let us understand like this. Let me take one more page. Okay, the first count, there are three counters. The first counter starts from 0000. It will reach 1001. Okay, so when this next state is 0000. This is q8. This is q1. q1. Okay, so this transition of high to low will trigger the second stage, which will start the count as 0000. So initially 0000. When this transition happens, the next count for the second counter is, this is the second counter, this is the first counter, and similarly we have the third counter. Okay, so the second counter count increments by one value, 0001. Okay, now this will remain 0001. Okay, the first counter continues the count. Okay, so it will reach 1001, and on the application of next clock pulse, the count will become 0000. This transition of q8 from 1 to 0 will trigger the second stage, and the second stage count it as a one clock pulse, and its count becomes 0010. Okay, like this it continues. That means for every one count of second stage of the second BCD counter, the first counter will count 10 clock pulse. First counter will count 10 clock pulse. When the second counter reaches the count of 1001, on the application of next clock pulse, that is when the first counter goes from 0000 up to 1001, and when it resets back to 0000, this transition of high to low will trigger the second stage, and the second stage will go from 1001 to 0000. This high to low transition of the second stage will trigger the third stage, and the third stage will go from 0000 to 0001. Like this it continues. Okay, so thereby the best point which acts as in clock pulse to the next stage is q8. So that's why we can see that q8 is applied as a clock pulse to the next stage. Similarly, for the second stage, which corresponds to 10 power 1 digit, the q8 is applied as a clock pulse to the third stage. Like this it continues. Okay, so like this we can interface n number of BCD ripple counters. Okay, this is for the up count. What should be the changes for a down count? Okay, very simple. Down count, as you can we have seen in a 3-bit binary down counter. For a down count, okay, yeah, here we go. The complement output, okay, here it is. The complement output, that is q dash, should be given as a clock input to the next stage. Okay, so with this modification, again here it is q dash given as a clock input to the next stage. Okay, so it starts from 1001 initially. Of course, when the counter is started, it will not start from 1001. It will start from zero initially. Initially it is 0000. When the the circuit turned on, so the next count will be 1001, which acts as a initial state for the down counter, BCD ripple counter, down counter. So because the complement output is applied as a clock pulse to the next stage, and at this stage what should happen is the complement output should be given as a input to the AND gate. Okay, and the output of the AND gate, okay, because when it reaches 0000, okay, so the next state should be 1001. That means it should go from 0 to 1. Okay, so for 0 to 1, one possibility is that output of the AND gate can be given to K input, which is the reset input, or else we can use a NAND gate. Okay, so what is the NAND gate does? 1 1 1, it will make it to 0. Okay, so the output 0 will, okay, no, it will reset to 0, reset q8 to 0. okay, should reset to 1. So thereby this should be an OR gate. Instead of an AND gate, we can make use of an OR gate and can be connected to J input. Okay, when both are 1 1, the Q8 will be set to 1. Q8 will be set to 1, and this way the down counter can be implemented. Yes, try to implement this using a what do you call the deed software, because it will give practice. You get familiar with the various types of counter circuit. Okay. Yes. Next is the synchronous counter. Okay. Of course, we have discussed basic binary counters. There is asynchronous counter. One of them is a what do you call ripple counter, because we apply the clock pulse only to one of the flip flop. Okay, in this synchronous counter, difference what we see is, just a second. Okay, what we see here is that still it is not fitting the page. Okay, yeah, here we go. Okay, this is a 4-bit synchronous binary counter. Okay, so binary counter means the initial count is 0000 up count. So what default when we say counter, we consider it as up counter until and unless we specify it as a down counter. Okay, so next state should be 0 for a 4-bit counter 0001. Since it is a binary counter, it will go from 00002 up to the final count of 1111. On the application of next clock pulse, the count should be reset back to 0000. Okay, fine. Here we go. So for a this synchronous counter, what will happen is the clock pulse is applied as a clock input for the all the flip flops, not like a binary ripple counter where the clock pulse is applied to only the one flip flop, and output of that flip flop is applied as a clock input for the next flip flop. No. Okay, so the clock pulse is applied to the all the flip flops. Again, one observation: the clock input is a negative clock flip flops. Clock input is a negative clock pulse. Why it is a negative clock pulse? Again, the same understanding. So when it goes from 1 to the clock, when it transitions from 1 to 0, that is falling edge. This falling edge will trigger the flip flops. Okay, so falling edge will force the, because we are we are implementing counter with normal output is given as input to the clock input to the next stage. Sorry, not a clock input. Sorry. So it's given as input to, of course taken as a feedback. So then since we are implementing the counter, normal output is considered, and the negative edge clock pulse is preferred. Okay, than the positive edge clock pulse. Okay, here we go. Okay, so observe this. There are 4 flip flops because it's a 4-bit synchronous counter. Clock pulse is common for all the flip flops. Okay. Yes. Now, if you observe the input for the flip flop. So one is the clock pulse that we discussed. Next is the the input. Okay. The input is, what we can see is a count enable. What is this count enable input? Okay, so if you see for the first flip flop, this is the first, second, third, and fourth flip flop. For the first flip flop, count enable input is given as a J and K input. For example, if both are 00, no change in the output, no change in the output of the first flip flop. But when it is equal to 1, when it's set to 1, output of the first flip flop will toggle. That means it becomes a T flip flop. It will toggle. Okay, so thereby initial condition, let us start with the initial condition of 0000. Okay, let us say count enable input is 1. This is here it is, they have used it as A1, A2, A3, and A4. Okay, what should happen to A1? A1 will change the state from 0 to 1. Okay, other flip flop output remains the same because it is yet to be applied. It is yet to change the state. Okay. Now observe this AND gate. Okay, the output of the first flip flop initially 0. Initially, before we apply the enable input, and count enable is also 0. The output is 0, which is applied as a input JK input for the second flip flop. This is the first, second, third, and fourth. Okay, so when the JK input for the second flip flop, if it is 00, output is forced to 0. That is A2 remains 0. Okay, the output of the first AND gate, first, second, third, and the fourth AND gate. Okay, So output of the first AND gate, which is 0, which is applied as a input for the second AND gate, and the output A2 is applied as a input for the second AND gate. 0 0, it remains 0 AND gate output. So JK input for the third flip flop is 0. Output A3 is equal to 0, which is applied as the input for the third AND gate, which is 0 0 again. A4 is 0, which is again applied as the input for the fourth AND gate. Okay, fine. Okay, so that means at the second stage, initially to start with, it is 0 0. When count enable becomes 1, what will happen is A is set to 1. Let me erase this and let me write it. Okay, yes, here we go. Okay, when the count enable input becomes 1, A1 is set to 1. Okay, when A1 is set to 1, observe the first AND gate, first AND gate. It is both inputs are 1 1. When both the inputs are 1 1, okay, what will happen is initially to start with, because we are applying the clock pulse. See, initially to start with, because we are applying the clock pulse to the the first stage, both inputs are 1 1. The first A1 will change the state from 0 to 1. Initial state was 0. Because of this, the input for the AND gate is first AND gate. First AND gate is 1 and 0 before 1 is applied. Okay. Let us say even 1 is applied. Initial state of 1 is 0. So because of this, input for the first AND gate is 1 and 0, whose output is 0 0. Okay, which will force the second, third, and fourth flip flop to remain at 0. That's right. Okay. Next, the output of A1 is 1. So the input for the first AND gate is 1 and 1. The output of the first AND gate is 1, which acts as an input for the second flip flop. Inputs are 1 1. A2 will is forced to change the state from 0 to 1. Okay, that means A2 will change it to 1. Okay, what should happen to A1? Please observe this A1. A1 is input is 1. That means when the input count enable input is 1, A1 is forced to toggle. Toggle means it was initially 1, it is forced to toggle to 0. That is A1 becomes 0. A2 becomes 1. A3 and A4 still they are 0. Okay. Like this it continues. In the next count, for example, A1 continues to toggle from 0 to 1 because its input is count enable, it's fixed. Okay. So for A2 what happens is that, so if you observe this, the output of A2 is 1, the AND gate output is 1, output of first AND gate is 1, which is applied as input for the second AND gate. Inputs are 1 1, output is 1. For a third flip flop, the input JK input is 1 1. A3 is forced to change to 1. A3 becomes 1. Okay, in the next, of course, in the next stage, of course, initially it is 0 0 1 1. Okay, next, when both A2 and A1 is 1 1, A3 is forced to change the state from 0 to 1, and these two will become 0. These two will become 0. Like this it continues till it reaches final count of 1 1 1 1. Okay, yes. When it reaches final count of 1 1 1 1, what will happen is, so let us say all the outputs are initially 1 now. All the outputs are initially 1. Okay, when the clock pulse is applied, when the that is okay, when the clock pulse count enable 1 is applied, A1 is reset to 0. A1 is set to 0. So this 0 propagates to the second stage 0, which will force the second stage to also change to 0. Like this, all the outputs ultimately becomes equal to 0. Okay. Of course, this will not happen in one cycle. So for this, what we have to do is we have to forcefully change the output to 0. That we can do. That preset and clear can be used to reset the counter to 0. Possible. Okay, so this is what is known as a 4-bit synchronous counter. So what we understand here is, okay, yes, the question is why these AND gates are required. Maybe we could have instead of using the AND gate, we could have directly applied 1 1. Both these inputs are shorted, we could have given it to 1 possible. Okay, but in this case, if it is continuously 1, A2 will continue to shift from 0 to 1, 1 to 0, like this. Okay, and if third stage is also given common input as 1, third output will change the state from 0 to 1, 1 to. Output of each stage should depend on the previous stage. Then only we'll be able to implement binary counters. Okay, so that's why we make use of a AND gate, which comes in the path of the feedback of the circuit, so that we can implement a binary counter up counter. What should be the changes for binary down counter is we should make use of a complement output. Complement output can be given as a input for the next stage. So then it should start from initial state of 0000, and the next state should be 1111, and this continues down count 1110. Like this it continues till it reaches a final count of 0000. Okay, so that's the 4-bit synchronous binary down counter. Is the same thing is explained here, for each stage, how it changes, it is explained here. Binary down counter. Okay, so for binary down counter, okay, so any other complement output, I can see one statement here. There is binary, I think I missed that. Yeah, binary down counter. The Except that the input to the AND gate must come from the complement output of the flip flop, not from the normal output. So AND gate input should be from the complement output, Q dash. Okay, Q dash. Yeah, that's all the difference for the what is known as a binary down counter. BCD counter. Okay, so what we discussed is a synchronous 4-bit synchronous binary counter. Next, modify the same circuit to implement 4-bit synchronous BCD counter. Okay, so let us up down. Okay, this is up down counter for BCD. This is up down both. I think this is up down counter is discussed here. Just a second, please. Okay, how do we get this? BCD up down counter both we can achieve. We need not change the output here. There is, instead of connecting no, next connect Q dash to this AND gate, not necessarily. We can implement both up and down counter in the same circuit. Let us look into this circuit. BCD up down counter, synchronous BCD up and down counter. Okay, 4-bit up and down counter. So for this, it must be BCD. I'll cross check again, because if they're explaining for okay, table yeah, BCD, correct, excitation table for a BCD counter. Yeah, here we go. Okay, okay, guess before we look into the circuit, let us look into the excitation table. Again, excitation table consists of two tables. One is the state table and the truth table. Truth table means input is applied and the output also can be seen. Okay, what are the various states of this excitation table? Okay, present state. This is a normal BCD counter. It should start from 0. There is a decimal 0. There is a 0000. On the application of next clock pulse, the count should become 1. That means it has counted 1 clock pulse. Next clock pulse, the count should be 2. Like this, it counts till it reaches a final count of 1001. On the application of next clock pulse, the output should be 0000. Okay, fine. Here we go. Okay. So for the present state, when the clock pulse is applied, the next state is given as a +1. So for example, 0 is the first state, next state will be 1. Likewise, for the final state of 1001, when the clock pulse is applied, next state should be 000. Very simple. Okay, so this is the state table. This is called as a state table. Okay, fine. So for this, the truth table part. What is truth table part? So now what is the requirement here is, okay, now the output, this output Y is taken from okay, in this diagram it is not shown. The Y is output Y. It is not shown in this diagram. Okay, what should be the output? Combination output. This is output from the combination circuit. Yes, I'll explain this, and when I discuss the diagram, we will discuss this. Okay, now for this flip flop, what should be the flip flop input? Okay, by the way, which flip flop is preferable? Okay, even if we make use of JK, we have to short it and give it to 1 to convert into flip flop. Sorry, to convert into T flip flop. Instead of this, one thing we can do. Okay, there is prefer T flip-flop instead of J. Advantage is that we need not give two inputs. At least that can be avoided. Okay? So prefer wherever only toggling operation is required. Wherever only toggling operation is required, we can straight away we can go for a T flip-flop. So the preferable flip-flop is the right candidate, right choice is T flip-flop. Here we go. Okay. So for a T flip-flop, inputs are T, only one input. There are four flip-flops. The inputs are called as a TQ1, TQ2, TQ4, and TQ8. Why this Q8, Q4? Because position. Okay, 8 position wise, 8, 4, 2, 1. Very simple. Okay, fine. Now let us understand how do we get this input. What should be the input? Okay? So for a present state of 0 to go to the next state, only the Q1 should change the state from 0 to 1. Only Q1 should change the state from 0 to 1. Okay. So the input for the first flip flop should be 1. And other input should be 0 because other flip flop should not change the state. It should remain 0. Very simple. Okay. Next, let's observe this. In the next state of 0001, both first and second flip flop should toggle. Both first and second, both Q1 and Q2 should toggle. Okay. So for this, both the input should be 1 1. Both the input should be 1 1. Very simple. Let us take one more example. Let us say, for example, from 0010, that is 2 to 3. Okay. Which flip flop should toggle? Only the last flip flop should toggle. The second flip flop should remain the same. So what should be the input for the first flip flop? It should be 1, and the last flip flop should be 0. Yes, if you observe this table, it's very simple, easy to guess. The first flip flop will always have the input of 1 1. Why? Because it will continuously toggle. If you see this, the present state and the next state, this Q1 should continuously toggle. As long as Q1 should continuously toggle, its input should always be equal to 1. Very simple. It is a toggle flip flop. It continues to toggle. Very simple. Okay. Next. Likewise, let us take one random case. Let us say, for example, okay, 1001 is the present state. Next state should be 1001. So only the first flip flop changes the state. Only the first flip flop should change the state. Other flip flop should not change the state. So what should be the the input for the flip flop? Only the first flip flop should be applied with 1. Other flip flop should have the input as 0. Very simple. It's okay? Fine. Now, how to solve this is very simple. The inputs is known. This as the output. Use the K-map and simplify the expression. Obtain the simplified expression for the input stage of flip-flop, that is TQ1, TQ2, TQ4, TQ8. Okay. So after simplification, we have the expression, and in this textbook, of course, it is assumed that we can solve it using K-map and okay. Yes, we can simplify it. Yes, there's one more. Unused states should be taken as a don't care terms. What is this unused state? Let us understand this one quickly. Okay. Now, when we write a K-map for this, how to write a K-map? Very simple. Let us take this is one function. For example, TQ8. Okay. So when we write the K-map for this, so what is the situation is? Let me take one more page. Okay. So the present state is can be written as that is Q8 to Q4, Q2, Q1, TQ8, for example. Let us say we are solving for TQ8. Okay. So TQ8 is 101. Last bit is 101. Okay. Last bit is 101. Other conditions are 0, 0, 0, 0, 0, 0. That means the first state is 0, 0, 0, 0. Next is 0, 0. Oh, okay, just a second. It should be from the next state, no? Not from the present state. Correct. It should be from next state. So this should be the input, not the present state. Present or next state. Guys, just give me a second and I'll clarify. Because excitation table, the output is equal to 1 and the counter state is 1. Okay. In this way, we can enable the next higher order. Okay. Flip flop 10 to 15 or don't care, that's fine. The BCD input should be simplified functions are okay. And OR gate, just a second, I think it is from the next state, the output. Yeah, here it is. this statement, the output is equal to 1 in the counter present state is 0 0. This way okay, fine, here we go. Okay, this is the present state. Yeah, here it is. That means present state, if it is 0 0 0 1, it will be 0. Like this, when the last state is 1 0 0 1, it should be equal to 1. Okay. Now for a 4-bit, see, it is a 4-bit function. How many cells are there in a 4-bit function? There are totally 16 cells in a K-map. What I'm talking is in a K-map, there are totally 16 cells. Okay. So the 16 cells means what we have written is only from 0 to 9. 0 to only 10 states. Still 6 more states are missing. That is from 1010 up to 1111. For this input, what should be the output? Because in a K-map, when we write zeros and ones, okay, we cannot leave the cells for 10 to 15. That is 8 9. This is 10 11. 12, 13, 14, 15. For these cells, we have to write something. What we should write? Whether we can write zeros or ones. Okay. Since for a BCD counter, the valid states are only 0000 up to 1001. Okay. Left out states from 10 to 415 should be considered as don't care. Okay. So we should enter don't care into the K map. Okay. And what are these values, guys? I think it is if this is 9, this must be 7. 0 1 1 1, it is 1, 7 is 1, 9 is 1, all others are 0. Where is 7? I think here it is 7. This is 7, this is 7, and 9. Which is 9? This is 9. Okay. So this is 0 actually. Here is this. Okay. So this is the K map for the TQ8. So this is also 0. Okay. So how to group this? Something like this. Group, no, not the don't care. Okay. Group these two. Okay. One and don't care. And similarly group these two, this one and don't care. Okay. So we can write the expression for TQ8 as you can see that here, when you write the expression for TQ8, we'll get two terms. Why two terms? Because we have two groupings. One grouping is okay, they have simplified this further. What is the simplification, guys? These four can be grouped. Why? Because this is 1, these 3 R's don't care. Okay. So to simplify the expression further, instead of grouping only this 1 and don't care, we can group these 4 terms. Okay. That is, the terms are 9, 11, 13 and 15 cells. Cell number 9, 11, 13, 15 can be grouped. We'll get one expression. Another grouping is only these two are possible. There's another possibility for this. We'll get one more expression from this. Okay. So likewise, we can simplify for TQ8. Similarly, we can simplify for TQ1, TQ4 in the same pattern. That is, TQ4 is here. That is why we will write TQ4 here. Write one more, one more truth KMF for TQ4. Okay, and simplify it. We'll get the expression as Q2 Q1. Similarly, TQ8, TQ2, Q8 dash Q1, and TQ1 is 1. This is very simple, because TQ1 should always be 1. Then only we'll get the output. Okay. What is this Y? Y is for the next stage. Okay. When the next stage is going to should be set to 1. Okay. That is, we have understood in the earlier BCD counter. When the first stage goes from 0 0 0 0, final state is 1 1 1 1. Sorry, I made a mistake. So final state is 1 0 0 1. On the application of next clock pulse, the count should go to 0 0 0 0. This should start this next stage. Next stage should go from 0 0 0. Initially it was 0 0 0 0. It should go to 0 0 0 1. Okay. So for this, the next state, it's an AND input. Output should be 1. If you consider this count, the final count of the first stage, only Q8 and Q1 are 1. So apply this Q8 and Q1 as the input for the AND gate, whose output will be 1. This 1 is applied as the input for the next stage. Okay. So that is considered as a transition, the clock pulse, which will trigger the second stage. Okay. So let us quickly see the the realization of this. Yes, 2 more minutes. Yeah, here we go. So this is okay, done. So that's why we see this, there is for Y output, it is equal to 1 only when both Q8 and Q1 are 1. If you consider the other conditions, Q8 and Q1, will never be equal to 1 together. It will never be 1 at the same time. Okay, both are 1 only when it reaches the final count of 1001. Of course, instead of AND gate, what we can do is, we can use NAND gate for Q4 and Q2. That's also possible. Use a NAND gate for the other way around, alternate way of implementing the, this next stage. That's also possible. No problem. There are various possibilities. So when you see this in realization is very simple from the same expression wise. Q for this is yeah, here it starts from here. Just a second. Q2. So for Q2, the inputs are okay. So this considers up and down counter also. That's this we need to discuss up and down counter also. So otherwise, the for the first stage, the input is 1, T input is 1. Okay, this anyway, I'll take up this in the next class. Okay, because we need to consider this up and down counter also, along with, because we are designing a both up and down counter. So the input stage slightly changes because of the up and down counter. I'll continue the discussion of BCD synchronous up and down counter using T flip flop. Okay, so, thank you. See you in the next class. Bye.
Thank you, sir.
Thank you, sir.
Yeah, bye.
Thank you, sir.